one possible reason why this hidden 90 degrees phase is relevant, I kind of realized now, is because it's all over the place, and I now I realized, I don't know if it's a mathematical convenience, but I think the reason is that it's only with that hidden phase that we make the operation reversible in itself. So if you apply Hadamard, it's another. That's here we're in the state one with phase zero. If you apply Hadamard, now it's this superposition, and if you apply Hadamard again, then you're here again back at where you started. Now look what happens if you apply uh, the H test one, which has a hidden phase of zero, right? So you apply it, right? And now, if you apply the same again, it really hasn't it really hasn't come back to its original state, because now the amplitude of this state is 180 degrees. So you actually need to apply it 4 times before you really go uh, to your initial state, including the phase, right? And I think that's kind of the convenience of having that hidden phase being 90, and that is something that I I was just playing with this right now, and I kind of realized, because I was doing the same with the Z gate. I was and say, with the Z gate. So if you're into a Hadamard position, you go into superposition, and now you apply a Z gate. Oh, let's just go like use the seed zero, right? So you've got the two phases are zero. Now you apply the Z gate, and then you've negated that phase. So now you're like minus 180 degrees. You apply it again, and you're back at square one. And this is because, again, this also gate has a hidden phase of 90 degrees. If I create the same gate without that hidden phase, so just the z-axis and 180 degrees, and I'll call that z test. So the same is going to happen. Basically, you apply the z test one, right? And it kind of does the same effect in the block sphere, but you've got to apply it. You've got to apply it 4 times until you really go back to that original state. That's where you were here, exactly right after the Hadamard. If you're putting the displacing here, you see that, yeah. And I think that's one of the things that I can come up with. It kind of seems to make sense. The utility of that hidden phase. But I'm kind of like, why does this really happen? The rotation just does this. Okay, it phases because it phases both components. So if you just rotate around the z-axis, it phases both components. But if you're adding that hidden phase of 90 degrees, then suddenly you're only phasing the one component. Yeah, well, maybe that is. So this is the way this looks like. Okay, down and up, and then this is okay, right and left. So when you're adding 90 degrees, it's interesting though. If you don't add that, then basically, I'm not sure exactly why this happens, but this kind of makes I mean, it makes sense experimentally. I mean, practically you can see it here, right? Just trying to think a little bit about. So it's a complex phase what we're adding here. If we're only rotating 180 degrees, which is kind of awkward because the blocks here. Oh yeah, because the angle is divided by 2. That's why. In the formula, boah, I don't know. Okay, I'll give it a bit of an extra thought as well, but that kind of makes sense. So without that phase, that's what I observed. The gate itself is not reversible, which is convenient, right? I mean, I'm not saying that it has to be. No, actually, it has to be, doesn't it? No, it doesn't have to be, but of course, it doesn't have to be. But then it's not its own inverse, and that's kind of the convenience of the Hadamard gate, that its own inverse. It's its own inverse. Um, I guess it's a practical convenience in terms of actual physical implementation. I guess so. Yeah. Let's see.